name is Professor Jae Sung Lee from Pohang University of Science and Technology. I think you are familiar with the Pohang Institute of Science and Technology, but we are in the process of changing name. So I'm saying Pohang University of Science and Technology. Professor Lee obtained his PhD from Stanford in 1984. Since then, for 2 years, from 84 to 86, he was with Catalytica as research fellow. He joined Pohang University of Science and Technology in 1986. I think his research areas interest are homogeneous and heterogeneous catalysis related to the C1 chemistry and also new catalytic materials.
Thank you, Chairman. You didn't introduce the title.
Okay, I'm going to introduce the title of this. Okay. Methanol synthesis from carbon dioxide hydrogenation over copper-based catalyst. Thank you for.
My presentation is related to the recent environmental catalysis, namely the global warming. Carbon dioxide has been known as the major contributor, major greenhouse effect gas, so-called, which block the radiation from the Earth and cause the global warming. And that what's happening, what's going to be happening, and according to the world scenario, by the middle of the next century, the global temperature will rise by 3 degrees Celsius, and then that will cause the rise of sea level by 65 centimeters. Then you might need the return of the Noah's Ark in Manhattan. There are a number of the technology available to tackle these problems. The first is to take the alternative energy sources which produce less or no carbon dioxide. Secondly, you either accelerate energy savings or increase the efficiency of energy conversion. And finally, the aggressive method is so-called carbon dioxide fixation. Namely, you actively recover the carbon dioxide from your stack and then convert it to the useful chemicals. And one of those technology is the catalytic hydrogenation, and this is the area that our catalyst people are related to this problem. The carbon dioxide, as we all aware of, is kinetically and thermodynamically very stable molecule. So in order to activate it, you need the potent reductant. And probably the most convenient reductant is dihydrogen. And indeed, many chemicals such as hydrocarbons or carboxylic acid, high alcohols, and methanol could be produced with using CO2 hydrogenation if you employ the proper catalyst. When you consider the CO2 utilization, you are talking about the large volume of the material. So when you select the target product, you have to consider if those product is absorbed by the market, and then those products should be related to the energy. And for those reasons, methanol has been considered the most promising target because their potential utilization in energy market. So this is what the Japanese saw. Japan, probably you know that the most active in this area. So this is this cartoon illustrates what they are thinking. So carbon dioxide is recovered from the stack and then separate probably by the membrane technology, and hydrogen comes from the water either by the electrolysis or water splitting using the solar energy. And this CO2 and hydrogen reacted in the high efficiency the heterogeneous catalysis catalyst to produce the methanol, which could be used as a liquid fuel. One other advantage of using methanol is their convenience for storage and transportation. And for example, in the region where you consume a lot of the energy, you can recover CO2 and liquefy it and transport the CO2 to the region rich in natural resources. And here you convert those CO2 to methanol and then transport it back to the energy consuming region. So in this sense, the CO2 could be served as the hydrogen energy carrier. So much for the advertisement. Let's talk about little science. Okay. So our target is hydrogenate CO2 to methanol. And the CO2 hydrogenation is closely related to the methanol synthesis from CO, because the usual industrial feed contain about 5 volume% of the CO2 in addition to the CO and hydrogen. And in spite of the process is quite mature, there are a lot of the fundamental questions which has yet to be answered. And one of them is that what is the primary source of methanol in synthesis with both CO and CO2 is involved. And most easy and obvious choice might be carbon monoxide, because it must be much more reactive than CO2. And this is what Boomer and Mori thought in 60 years ago. So CO2 participates in the reaction only after first converted to CO by reverse water gas shift reaction. And people thought that the role of CO2, in addition to the secondary reactant, was the promoter to control the surface composition, oxidation state, and dispersion of copper catalyst. And although this mechanism was not based on any experimental evidence, it was accepted widely because the intuitively is quite natural. But apparently Russians didn't agree on the idea. So the Rozhovsky in the Topchev Institute of Petroleum Synthesis in Moscow, by means of the kinetic method and also isotope labeling technique, demonstrate that actually the methanol comes from the CO2 instead of CO on conventional copper zinc oxide catalyst. And it took just about 10 years for this information crossed the Iron Curtain, and 10 years later, the people in ICI tested the same experiment on their commercial catalyst under commercial temperature and pressure, and they demonstrate that over the wide range of CO to CO ratio, almost 100% of the methanol come from the CO2 instead of CO. Only in this small region, the contribution of CO was significant. So the new mechanism shows that CO2 is primary reactant and CO was secondary reactant, and additional load of CO was promoter to scavenge adsorbed oxygen. So this experimental result seems to me rather convincing, but still matter is not completely settled. Particularly the interesting controversy is probably related to this problem is the effect of the CO-CO2 ratio on the methanol synthesis rate. Clear and his co-workers shows that as the CO2 concentration increase in the syngas, the methanol the synthesis rate increase first, shows a maximum, and then decrease again. And they explain this phenomenon based on the assumption that the CO is the primary reactant, that you are expecting this type of monotonous decrease. But if you use the pure CO, you deactivate the catalyst because they believe that some oxidized copper species is the active species. But the Kung at Northwestern started the same reaction at the batch reactor, and they measured the initial rate of the CO2 conversion, and they found that as the CO2 concentration increased, they saw the monotonic increase of the methanol synthesis rate. So the Kung proposed the various reasons that why their results are different from the Clear, and one of the more reasonable explanation is the effect of water. Namely, what you are expecting is increase of the synthesis rate as the CO2 replace CO, but because CO2 hydrogenation produces the water will deactivate the catalyst and deactivate the reaction, so you see the decrease of rate. But if you look at the slope of this increase, in this case and in this case, you will see that there must be some other effect other than the water. So with this background, we thought that it might be useful that in order to understand the CO2, the fundamental aspect of the CO2 hydrogenation, it might be useful to compare the reactivity of CO hydrogenation and CO2 hydrogenation over the same copper zinc oxide catalyst. So we prepared the catalyst according to the conventional co-precipitation method. And in this talk, I only concentrate on copper, zinc oxide, and alumina according to this composition. Okay. And reaction was studied, conventional the flow system, high pressure, and with the online gas chromatographic analysis capability. So in the next few slides, I'd like to show you the difference in reactivity between CO2 hydrogenation and CO hydrogenation. The first one is the mode of reaching steady state. In CO2 hydrogenation, you'll see no change in selectivity, very little change in the activity. So after about 4 hours, you can maintain the steady state. On the other hand, the CO hydrogenation, the behavior is very complex. You see the very complicated change in the initial 20 hours. Only after 20 hours, you see the steady state rate. But the selectivity didn't change appreciably. We test the effect of hydrogen CO2 ratio in both CO2 and CO hydrogenation. The hydrogen promotes the reaction, as can be seen here, but if the slope was much higher in the case of the CO2 hydrogenation. If you look at the methanol selectivity, CO2 hydrogenation show the increased the selectivity as the hydrogen pressure was increased. In the other hand, the CO hydrogenation, the hydrocarbons was formed at high hydrogen CO ratio, so decreased the selectivity a little bit. If you compare the selectivity pattern a little more closely, CO2 hydrogenation always produced about equal amount of CO and methanol. On the other hand, the CO hydrogenation produced some significant amount of CO2 and also the hydrocarbon. So if you compare the selectivity, the CO hydrogenation always give you the better the selectivity than CO2 hydrogenation. Now we test the effect of temperature under the same condition. Okay, if you compare the rate of methanol synthesis with CO and CO2, in the whole region, CO2 hydrogenation gives you the higher rate, and those difference was the greater at low temperature. Notice that this scale is the logarithm, and at this temperature region, CO2 hydrogenation proceeds more than 1 order of magnitude faster than CO hydrogenation. At higher temperature, those two rates are almost equal, or sometimes the CO hydrogenation becomes greater. And the maximum is not due to the loss of activity at high temperature, but because of the loss of selectivity, namely CO2 hydrogenation produces a lot more CO at high temperature. On the other hand, CO hydrogenation produces a lot more hydrocarbons at higher temperature. And this is nothing to do with the theoretical thermodynamic equilibrium. So this is the kinetic evidence that CO2 probably is the primary reactant because it converts to methanol much more faster than CO. We also test the effect of CO2-CO ratio. Okay, as the CO is replaced by CO2 at the increasing proportion, you see the increase in the rate of the methanol formation. But if you now decrease the space velocity or flow rate, the effect of CO2 composition become more and more smaller. And if you decrease the flow rate further, now you see the strange behavior. First, increase in the methanol synthesis rate, and then decrease at higher CO2 concentration. So you see the both effect observed by Clear and Kuhn for the same system when you change the flow rate. So this we try to eliminate some artifact. The one possibility is thermodynamic equilibrium, but it was not the case, as can be seen here. The other one is the two syntheses from CO and CO2 require a different amount of hydrogen. Because the hydrogen effect is quite significant, we now varied hydrogen partial pressure according to this stoichiometry. Okay, still at the higher space velocity, you see the monotonic increase of the methanol synthesis rate. But if you decrease the flow rate, now you see the peak in the middle. I like to draw your attention at this point that the pure CO, we usually employ the CO containing about 250 ppm of CO2 as a byproduct. Now, if you use the purer the reagent grade CO containing less than 50 ppm of CO2, the synthesis rate decreased substantially, which tells us that the pure CO, extremely pure CO, is very unreactive under this reaction condition. So what contributes this difference in behavior according to the flow rate? One candidate might be the water, because that's what the Kuhn proposed. So we measure the concentration of gas phase water by TCD and got this result. So when this data obtained at the same time, okay, these two cases which showed a very different behavior, shows almost the same water concentration in the gas phase. So it tells us that there must be another factor which contribute to this difference. So what is the difference? One thing we noticed that now under those two space velocity, you form more methanol, but you don't see any significant change in water concentration. This means that extra methanol comes from the synthesis which does not produce water, namely CO hydrogenation. So under those conditions, relatively more CO is consumed. So the gas phase is now richer in CO2 concentration. That might be the shift, the concentration of adsorbed oxygen species. So my hypothesis was that at the higher flow rate, you have the increased oxygen coverage as the CO2 concentration is increased, like this. But at the low flow rate, because of the difference in the gas phase composition, you'd have the steeper the change in oxygen concentration. There must be some optimum level of the oxygen coverage, say 0.5. And if you hit this optimum in the middle, you would see the maximum in the middle. If you do not hit on the whole region, you don't see any peak. So this was just the hypothesis, but the 2 weeks ago when we have the international CO2 workshop, in Daejeon, the CITO of the National Institute of Environment and Resources, he presented this data. Okay, they use a different kind of the catalyst or different loading or different reaction condition, and they titrate the surface oxygen. And this is the oxygen coverage, and this is the methanol formation rate. They found that indeed the methanol synthesis rate shows the maximum in the coverage about 30%. So although this is the different set of reaction condition, this is one evidence supporting that this hypothesis. So in this respect, the effect of the water, as you see here, is as a promoter, namely it promotes the water gas shift reaction to form CO2, but in this region, effect of water is just suppress the reaction rate. And this is reflected in effect of space velocity, namely in CO2 hydrogenation. If you increase the space velocity, you see increase the methanol synthesis rate because there's less concentration of water. In case of the CO2 hydrogenation, you see the decrease because in this region you have a promoting effect of water. I have the 2 more slides which shows the little bit of characterization. Both CO2 and CO hydrogenation didn't show much change in the bulk property, namely in the bulk you have the zero-valent copper. On the other hand, after reaction, we did some temperature programmed reaction study, and after CO hydrogenation, you see single peak like this. After CO2 hydrogenation, you see the larger peak showing more oxygen on the surface and also other species. I'm tempting to assign this some oxide species, but at this moment, I don't take the risk to do that. The difference is that now when you change the composition, if you start from CO to hydrogen and replace those CO2 with CO, you see this kind of behavior. And for example, in this case, this is the fresh catalyst. So if you play with the only CO2, you don't have any deactivation. But if you start from the CO, once the catalyst see the pure CO, you see always a deactivation. It does not reproduce the weight. So as a conclusion, we have some evidence supporting that the CO2 is the major primary reactant for the methanol synthesis of copper zinc oxide catalyst. We observed both phenomena observed by Clear and Kung for the same catalyst. The difference seems to be a difference in the effect of water and also the surface concentration of oxygen. And it seems to be the CO2 hydrogenation modify the copper surface to the more oxidized state, which seems to be more active than fully reduced state. Thank you for your attention.
Any questions?
When you monitor compositions under your different reaction conditions, especially related to space velocity, is your water-gas shift reaction at equilibrium under all conditions? Or is it non-equilibrated at high space velocities, but at equilibrium at the low space velocities?
The second one.
So when you move to high space velocities, it is not equilibrated.
Right.
Could that somehow be the reason that you can modify and regulate the amount of water and adjust it internally?
Yeah, that's what I'm
I have a question about the oxygen species on the CO and zinc. You write down all star. There is O minus or molecular oxygen. What kind of oxygen species can you expect in your catalyst?
I think it is also the controversial question, but that oxygen, which could be the titrate out by N2 titration. Okay, the way to determine the surface oxygen is that if the surface is covered by those species, you cannot titrate that side by N2 titration, but okay. So people say it is some O minus species or some neutral oxygen species, but I cannot tell which species it is. But you can determine it by the oxygen titration, the N2 titration.
Any other questions? Well, I think we are just on time. Let's thank Professor Lee for his excellent presentation.